Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, uAbutiwa Sos Ugobela Wemet. And without any further ado, let's look at these questions that we have here. Okay, so we have question 2, still on atomic combinations. It says, consider the following chemical equations, and then we can see we are given 2 chemical equations here. Then 2.1 says, define the term covalent bond. So quickly, let's run to that. We're going to say a covalent bond is the sharing of electrons between 2 atoms to form a molecule. So that's how we are required to define the term covalent bond for 2 marks. Then let's move. We have 2.2. It says write down the Lewis structure for the CH4 molecule. Now looking at this, we can see that this molecule is formed out of 1 atom of carbon and 4 atoms of hydrogens. And then since we know that our carbon is more electronegative, we know that the carbon will be our central atom, and then the hydrogen atoms will just be surrounding this carbon atom. So let's draw. We have our carbon, and then looking at our carbon, we can see that it is in group number 14. And then we're looking at the Roman figure, we can see that it has 4 valence electrons. So these are the valence electrons that we're going to put in here. 1, 2, 3, 4. And then hydrogen is in group number 1, meaning it only has 1 valence electron. So we just need to attach it there like that. And then also remember the fact that it is coming with that 1 valence electron. So there it goes. And then it bonds to that one. And then just like that, now you have your Lewis structure for the CH4 molecule. And then as we can see, the carbon atom now has 8 electrons around it, 8 valence electrons around it, which now makes it a stable atom. Right. Then let's move to 2.3. 2.3 says, consider the bonds C to H. So the carbon bonded to a hydrogen and the oxygen bonded to a hydrogen. Now they're asking which bond has a longer bond length. Give a reason for your answer. Now, before you answer this one, there's a particular relationship that you need to know with the periodic table, which is your atomic radius. So this is between which one, between the carbon and the oxygen, has a larger atomic radius. Right, but then we know the relationship of the atomic radius with the periodic table is that the atomic radius increases as we go down the periodic table and then decreases as we go across the periodic table. Right, so this is the atomic radius. So atomic radius increases as we go down the periodic table, but decreases as we go across the periodic table, meaning from left to right. So if that is the relationship, let's look at our carbon and our oxygen. As we can see here, it is in the same row. Let's say it is in the same period, right? And then this is our carbon, and then this is our oxygen. If we say the atomic radius decreases as we move along or we move across the periodic table, that means we are expecting the atomic radius of the oxygen to be smaller than the atomic radius of the carbon. Right. Now, obviously, the one with a larger atomic radius is the one that will produce a longer bond length. So that means looking at that, it obviously has to be our carbon. So that means that the bond C to H, the bond C to H is the one that has a longer bond length. So we are going to say that C to H, and the reason is what? The carbon atom has a larger atomic radius than the oxygen atom. So that's it. So the reason this bond now has a longer bond length, it's because the carbon atom has a larger atomic radius than the oxygen atom. So that means this one will have a longer bond length, while this one has a shorter bond length. Now in 2.3.2, they're now asking which one will be stronger, right? Now, when it comes to bond strength, what you need to realize is that bond length is inversely proportional to bond strength, right? Now, what is the meaning of this? So that means the shorter the bond length, then we expect a stronger bond strength, right? So the shorter the bond length, the greater the bond strength. So since we have discovered that this one has a longer bond length, and then this one has a shorter bond length, then obviously the one that will have a stronger bond strength is which one? The one with the shorter bond length, which is O to H, right? So just like that, we've answered those questions. So it's very crucial that you understand those relationships there. I will be doing a lesson video just going through those relationships and everything that you possibly need to know when it comes to atomic combinations, grade 11, right? Then now let's proceed to 2.4. 2.4 says how many lone pairs of electrons are in the central atom of the H2O molecule. Now, the way to answer this one is number one, let's start by drawing that H2O molecule using our Lewis structure so that we can clearly see everything. So that's 1, 2, 3, 4, 5, 6. So 6 because oxygen is in group number 16 and therefore has 6 valence electrons. And then if we are to attach our hydrogens here, we know that the hydrogens will attach where there's only one electron, right? And then there it goes. There it goes. Now, to count the number of lone pairs, now the lone pairs, we know these are the electrons, 2 electrons of the same kind that are attached to a particular atom. So as we can see here, this is a lone pair because as we can see, these 2 electrons are of the same atom, oxygen. And then also here, these 2 electrons are of the same atom, which is still the oxygen. So these are what we call the lone pairs. And then how many pairs of this are here? So as we can see, it's 1, 2, right? So remember, it's a pair, right? So there are 2 pairs of the lone pairs on the central atom. Remember, our oxygen, because it is more electronegative than the hydrogen, than this hydrogens, then it means it goes as the central atom. So that means answering 2.4, we're going to say we have 2 lone pairs, right? We have 2 lone pairs, as we can see from here. Then in 2.5, they're asking us to write down the formula of a substance in reaction 2 that has a dative covalent bond. Now, when we look at reaction number 2, we can see that this is a reaction to form a dative covalent bond, mainly because we are reacting with a hydrogen ion here. So this hydrogen ion is the one that we say it has 0 electrons, because remember the plus here means that it has gave away its electron. So this is a hydrogen ion, and then since it has an empty orbital, an empty valence electron orbital, that means it will have to receive both of its electrons from the nitrogen in the ammonia there, right? So which makes it a dative covalent bond. The substance that forms the dative covalent bond is obviously this one here. So it is the product. So that's where we form the dative covalent bond. So for 2.5, since they're saying write down the formula, we're going to have to write NH4 plus. So we call this the ammonium ion, right? So it's the NH4 plus. Then 2.6 says the NH3 molecule is a polar, but the CH4 molecule is a non-polar. Explain this observation. So they want us to explain why the NH3 is polar and the CH4 is non-polar, right? Now, when it comes to that, this is how you are expected to answer that question, right? So when it comes to so this is 4 marks. So meaning explaining on NH3 will give you 2 marks, and explaining on CH4 will give you 2 marks as well. So with the NH3, we're going to say the nitrogen atom is more electronegative than the H atom, right? But the NH3 molecular shape or geometry. So remember, geometry is a shape. So the NH3 molecular shape or geometry is asymmetrical, right? So we know having to consult our VSEPR meant to say, we know that the shape that is formed out of this is asymmetrical. So that's 2 marks for saying that. And then now we go to CH4. We say the carbon atom, again, is more electronegative, than the H atom. So how do I know that this one is more electronegative than that one? I'm only focusing on the numbers here. So if you can check here, the carbon here versus the hydrogen. So you can see that this one is a bigger number than that one. And even if you were to compare the number on the nitrogen there, and then compare it to that hydrogen, you can see it's still a bigger number. So that's what I'm using there. I'm using those numbers, the electronegative values, right? Then C atom is more electronegative than the H atom. But then you have to know the CH4 molecular geometry is symmetrical. So symmetrical. Right. So because this one is symmetrical, then it makes your CH4 to be what? Non-pole. Remember, if it's symmetrical, we say there's an even distribution of the electron density, right? So here there's an even distribution of the electron density, making it non-pole. But then if this one is asymmetrical, that means it is polar because there's an uneven distribution of the electron density, right? So asymmetrical always leads to a polar molecule, and symmetrical leads to a non-polar molecule, right? So that's how you are supposed to explain that. So with all that being said, guys, please press the thumbs up button if you've enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.